Okay, so here's what we were talking about last time. We were talking about Jordan canonical form. So remember the ideas we're taking matrices, some matrix A, right, and we're conjugating it, right, or we're looking to view it as a conjugate, same thing, really. Right, and the idea is that conjugations, of course, being a change of basis, here's the corresponding change of basis matrix. We're hoping to be able to, for all matrices, do look, in an ideal world, we'd like to diagonalize. That's what we're kind of fingers crossed hoping for. But since that doesn't work out, we can't always diagonalize. We would like to always at least be able to achieve something, pretty close to diagonal, if at all possible. So the result that we ended with is, and it takes a long time to even state the result, for all matrices, by way of conjugations, aka change of basis, you can put the matrix into Jordan canonical form. Now, let me remind you again, real quick. We spent a bunch of time talking about this last time. I don't want to go through the whole thing again, but so what is Jordan canonical form? That consolation prize that you can always do when a matrix is not diagonalizable. The large scale structure is that there are these things called eigenvalue blocks. Well, I call them eigenvalue blocks. The book doesn't give them a name. Eigenvalue blocks because the diagonal entries are the eigenvalues and the dimensions are the multiplicities. How nice. Inside of the eigenvalue blocks, there are more blocks. Inside of the eigenvalue blocks, we have, let's see here, little smaller blocks also on the diagonal. Called basic Jordan blocks, and those basic Jordan blocks inside of them, again, always the same thing. You always have the you always have the corresponding eigenvalue on the diagonal, and then just one just above the diagonal. Okay, so that those are the rules, right? That's remember we were talking about how there's kind of an analogy of sorts between this Jordan form thing and reduced row echelon form. It's different contexts, right? We're interested in fundamentally different things. We're interested in the underlying linear transformation, not in some sort of set of solutions, right? So we're doing conjugations to preserve the underlying linear transformation, not row operations to preserve the solution, right? So it's a different context. But just like with reduced echelon form, there's a bunch of rules that define what the form is. Like, what does it look like, right? It's a very different set of rules here than it was for reduced echelon form. Okay. We saw some examples last time. Okay. So moving on from there. So there's a weird discussion that we have to have, and that is about rearrangements. And it turns out, and I'm going to show you an explicit example of this, but you can rearrange the blocks. Right? Remember, reduced echelon, Jordan form is made up of blocks that are all on the diagonal, but without too much trouble, you can shuffle those blocks around, rearrange the blocks. And specifically, the way you're going to do that is by reordering the basis vectors. So why we care about this is going to reveal itself in a couple of minutes. First thing I want to show you is an example of what that looks like. So here we go. There's a bunch of details that are involved in this little demonstration, so bear with me on this. Okay, so we've got some matrix. And keep in mind, matrices represent linear transformation. So there's some underlying linear transformation, T, that we're talking about here. And, T. Here's our underlying linear transformation. I'd like to be able to talk about this underlying linear transformation, perhaps in different languages, using different bases, of course. Right? So here, I'll leave that. So same linear transformation. That's not going to change for any of the discussion in this example. We're always going to be looking at this same underlying linear transformation. Okay. first thing I want to do is talk about its matrix with respect to this basis, script V. All right, I'm asserting that the matrix with respect to that script V basis is this. Let's just say. And the question is, if I then take a different basis, if I take this basis and say, I want to talk about that same linear transformation, mind you, I'm not changing the linear transformation. Just, I want to understand it now with respect to a different basis. And I claim that what you get for this script W basis is you get that matrix. And I'm going to show you exactly where that comes from. But notice that this does what was promised, right? Look at the blocks that we have in here. There's 3 blocks. Well, I guess 4, maybe, depending on how you look at it. So there's 2 eigenvalue blocks. And then inside of the first eigenvalue block, there are 2 Jordan blocks. So count that however you want. Notice down here, the eigenvalue block, well, I mean, it's moved down here instead of up there, but it's still the same eigenvalue block. The blocks inside of it have been rearranged, but it's still the same 2 basic Jordan blocks inside of that eigenvalue block. This eigenvalue block with eigenvalue 6 is still there. It's moved. It's up here instead of down. But the blocks haven't changed. They've just been rearranged. Okay. All right. So now let me point out another detail here. The bases, looking at that basis versus this basis. Notice how it's the same 5 vectors. Right? I've just reordered the basis vectors. And you'll notice another thing. This pair, V1 and V2, stayed together in the reordering. Right? And notice, this pair of V1 and V2, they were the first 2 vectors there. This block was in the first 2 rows, first 2 columns there. When I reordered putting these first 2 vectors as now the last 2 vectors, notice now that same block has moved over into the last 2 rows, last 2 columns. Right? So, wow, what are the odds? Is that a coincidence? Not a coincidence, you probably expect. This vector stayed put. And notice that this Jordan block that's in the sort of the 3rd row and 3rd column remained also 3rd row, 3rd column. Okay. And then lastly, of course, these 2 vectors went from last to first. The corresponding block here went from, you might say, last to first. Okay. All right, so weird. Now, does that always work? How does what's the connection? How do I show that a certain reordering of the basis vectors results in shuffling, rearranging the blocks accordingly? And it's 2 different ways that you can think about this. I'm going to point out what those are. One thing is you can literally write down the change of basis matrix. Right? We know these 2 bases. You can explicitly write down that change of basis matrix and conjugate. It's what I would call the brute force approach. You could totally do that. I'm going to leave that as an exercise for y'all. I think everyone should do that. Once, go through and just, you want to see how that plays out. But it's just a matter of doing it. What I want to do is this second one, I'm going to show you how to do this part, and that is interpret each one of these matrices as, in fact, a list of equations. Don't forget, ultimately, that's what a matrix is. Right? The columns are telling you about the images of the basis vectors. So that's a bunch of equations. So for each matrix, we're going to write down what are those equations, and then we're going to note that they're exactly the same 5 equations. Okay, so let's do that part. Coming back up here. Okay, let's take these one matrix at a time. Look at that first column. Columns are images of basis vectors. specifically, this being the first column, this is telling me the image of the first basis vector. So that column is telling me what T of V1 is. Now, it's not telling me explicitly that T of V1 is 2, 0, 0, 0, 0. That's not what it is. It's that these are the coefficients of T of V1 with respect to that basis. So let's write that out. It's telling me that T of V1 is 2 V1 plus 0 V2 plus 0 V3, a bunch of more zeros here. So let me just keep it compact. It's telling me 2 V1. Okay, so now just some real quick highlighting. We're looking at the first column, therefore I'm getting the image of the first basis vector. Okay, these coefficients here are what I'm multiplying by those same basis vectors. So the basis vectors V1 through V5, the yellow numbers are the coefficients in taking a linear combination of V1 through V5. Okay, so that's all 5.3. That's just a quick reminder of how 5.3 works. How do matrices represent linear transformations? The columns are the images of the basis vectors. Okay, so along those same lines, let's write down a couple more equations. This tells me T of V2 is equal to 1V1 plus 2V2. And now let me just say dot, dot, dot. I could look at the remaining 3 columns, and that's going to give me another 3 equations. Okay, is everybody on board so far? Okay, now my assertion was that if I write down the same things for this matrix, let's write down those 5 equations, that it's going to be the exact same 5 equations. And at a glance, it doesn't look like it because you see, well, come on, they couldn't possibly be the same. That's a 2 and that's a 6. So they're clearly not the same, right? Well, the equations are not in the same order, but they are the same 5 equations. So let me show you where to find these 2 equations in this list. They're over here. They're these 2 columns. So let's explicitly write that out. Take them one at a time. Let's look at that column right there. Now, that's telling me about an image of a basis vector, T of something. Notice, of course, this is the 4th column, so this is telling me about the image of the 4th basis vector. Not the 4th basis vector from up there, though. That's the V basis. We're not using the V basis. We're using the W basis. Right, so it's not V4. The 4th column tells me about the image of the 4th W basis vector, which is V1. Right? So let's keep writing. So T of V1 equals, so now as we go through here, keep your eyes on, for comparison purposes, keep your eyes on this equation right there. We're going to end up reproducing that same equation. Again, doesn't look good at the very first. You look at these numbers in this column, and you see, well, there's a 0 and a 0 and a 0, and up here we started with a 2. Well, that's not the same. Well, yeah, right, of course, but we're taking a linear combination of different basis vectors. These coefficients here are coordinates in a linear combination of those vectors. So, going through the list, we have 0 V4. No need to write that down. 0 V5. No need to write that down. 0 V3. Again, with the 0. 2V1, there it is. Right? So 2V1. And then lastly, 0 V2. So again, no reason to write that down. So lo and behold, same equation, right? So this column in that matrix gives me that equation. this other column in the other matrix gives me that equation. Same equation. Now I'm going to leave it as an exercise for you all to, again, fill in, write down what the rest of the equations are for this matrix. It's 5 equations total. Fill in the remaining 3 equations from the upper matrix up there. Again, 5 equations total. And mix and match, and what you'll find is it's exactly the same 5 equations, just, in a different order. And that's all. How we doing? Any questions? Everybody on board? All right. Yes? Say it one more time. I'm sorry.
Those factors, if you want those factors into the linear transformation, those transformations into the matrix, like go backwards.
I'm not quite following your question. I'm sorry.
So you have the equations in purple. Take those equations and turn them into the matrix.
Yeah, I mean, sure. So one way you could, if you want to, you could think about how to, suppose I know this upper matrix and I want to figure out what this lower matrix is. One thing I could do is take the upper matrix, write the 5 equations, and then reorder the equations based on how did I reorder my basis vectors. Then don't forget, you also have to reorder the terms in each equation based on how I'm reordering, well, of course, that same basis, right? And then those equations produce that Jordan form. Absolutely. Was that your question?
Yeah.
Okay, cool. Okay, so there's an example of a rearrangement of blocks that comes from a reordering of basis vectors. Now, don't overinterpret from this, so I'm not saying that whenever you reorder blocks, that will automatically, said it wrong. When you reorder the basis vectors, does that automatically rearrange the blocks? And no, it doesn't. In fact, you got to be really careful when if you do want to rearrange blocks, you can't just shuffle around those basis vectors however you want. Notice, in order to keep this block actually a block, right? I've got to keep V1 and V2 together in the list, and furthermore, I've got to keep them in that same order. If I were to put V1 over here and V2 over here, well, then I just tore the whole thing apart, and now I've got a huge mess all over the floor. Right? So you got to keep, in some sense, the basis vectors corresponding to a block. You've got to keep them together and in that order that they started in. But however you want to rearrange the blocks gives rise to a reordering of the basis vectors that will accomplish that. Okay. All right. So why are we talking about this? All of this comes in relation to a question that we need to ask, which is kind of analogous to the, keep in mind we were talking about reduced row echelon form, and reduced row echelon form was unique, right? If you give me any matrix, you can always put it into reduced row echelon form, and furthermore, for any given matrix, there is exactly one reduced row echelon form. So, natural question to ask about Jordan form. Is Jordan form unique? Sadly, no. Jordan form is not unique. And in fact, here's an easy counterexample, right? We started with some initial matrix. Whatever. I don't know what that original matrix was, but it's conjugate to this Jordan form. But just by doing this change of basis, reordering those basis vectors, I see that Jordan form is also similar to this Jordan form. So here's clearly, right in front of us, 2 Jordan forms similar to the same original matrix. So it's a little bit bad news. Jordan form is not unique. So, that's too bad. However, this is the only form of lack of uniqueness. Right? So, ignoring rearrangements. Ignoring the fact that, well, of course you can shuffle blocks around however you want. Just, reorder the basis vectors accordingly. That'll shuffle the blocks as we saw on the previous page. So, other than that, other than rearrangements, every matrix can be put exactly into one Jordan form. Exactly one. Okay, so all this rearrangement business, again, sort of unfortunately, that's well, we have to bring that up and talk about how that works and see what that means in order to be able to address the question of uniqueness, which, again, strictly speaking, the answer is no. But there's a really nice relationship between these, non-unique Jordan forms, and so so you can almost kind of see the the lingo here. We say up to rearrangement, ignoring rearrangements. But you can think about it, rearranging the blocks. Well, that's it's the same Lego pieces, but just kind of moving them around. It's not really changing it very much, right? And so, in a way, it's like Jordan form is unique. Except for, of course, this one little bit of silly business of, shuffling blocks. Okay. All right. So what can you do with this? Here is a nice example. Let's suppose that I do a similarity and find that some matrix is similar to this, and then maybe somebody else doing their own work, they conclude that that same matrix is similar to this. Is it possible that we're both right, or did necessarily it must be someone must have messed up? And the answer is someone must have messed up, because let's break down what these Jordan forms are. Here is a basic Jordan block, and here is the other basic Jordan block in that form, whereas there's just one great big basic Jordan block over there. Right? These two different forms, not only are they different, but they are simply not rearrangements of each other. And because they're not, there's no way that you can shuffle two small things and make a big thing out of them. That's just not how it works, right? So these two blocks do not rearrange to make this one big block. These are not rearrangements, and therefore these are not similar. Because every matrix can be put into exactly one Jordan form modulo rearrangements. Okay. All right. Okay. Let's see here. Moving along. So let's talk about eigenvectors. What does Jordan form have to do with eigenvectors? Remember, Jordan form is our consolation prize to diagonalizability. Right? Diagonalizability has a lot to do with eigenvectors. Eigenvectors are your diagonalizing basis. That's how you diagonalize, is by having eigenvectors. So what about Jordan form? Turns out there's a very nice and simple relationship. I just have to remind you all of a couple of details. Don't forget, Jordan form is the way we represent a linear transformation with respect to a basis. That basis, don't forget, I've given that a name. I like to call that the Jordan basis, or a Jordan basis. It's not unique. There are many of them. So let's itemize. So here's those vectors, the basis that goes into Jordanizing a linear transformation. Let's say those vectors are v1 through vn. Okay. So remembering that, again, the columns tell you about the images of the basis vectors. Right? So with that in mind, recall, we can literally look straight at a list of numbers in a column of Jordan form and infer correspondingly an equation. Here we are looking at let's say the ith row, whatever row it ends up being, the ith row. That I is therefore going to tell us about the image of the ith basis vector. And let's see here. The coefficients are mostly zeros. Notice that most of these terms are not there. There is a single non-zero entry in this column. By the way, this being in Jordan form, that's a diagonal entry, which means that the row number is the same as the column number. So this one lambda right there, the ith entry, what that's telling you is that we have lambda times the ith basis vector. Right? So again, this is just 5.3. Again, the columns are telling you about the images of the basis vectors. Input basis tells you which basis vector. The column themselves are coefficients in linear combinations of the output basis vectors. And notice what this equation turned into. It's kind of remarkably convenient. And I should leave here. Let me do it like this. This ith column tells you T of VI is equal to lambda VI. In other words, T of VI is a multiple of VI. In other words, VI is an eigenvector. You can see it right there in the Jordan form itself. Yeah? Neato. What about the others? What about, let's take the jth column, some other column. Notice conspicuously I picked here the first column that intersects with this particular basic Jordan block. Right, so let's look now at a different column, not the first column. Seeing as it's not the first column, well, it's going to intersect with this just above the diagonal. Which means that there are two non-zero terms in this column. There's that one just above the diagonal, and there's the lambda that's on the diagonal. Which gives me then two terms over here. Let's see here. I have 1 times the vector just before the jth vector, namely Vj minus 1. And then, let's see here, color choice, we'll use green here. This lambda then times the Vj, the jth basis vector. So looking at that equation, now again, that column, just given what that column is in this Jordan form, that column gives you this equation. And that tells you Vj is not an eigenvector. Right? It's not, by the way, just that, it doesn't evidence itself as an eigenvector. You can explicitly see this is not an eigenvector. T of Vj would have to be a multiple of Vj. I see lambda Vj, that is a multiple of Vj, but then in addition to that, I've got another term that I know is not a multiple of Vj because these are basis vectors, they have to be independent, so this sum just cannot be a multiple of Vj. Okay. Alright, so neat punchline then. When you are looking at Jordan form, for every block, let's see, let me color code this. For every block, there is exactly one first column that it intersects. For every such first column, there is exactly one corresponding basis vector, which is therefore an eigenvector. So, nice little one-to-one correspondence among these Jordan basis vectors. For every block, there is an eigenvector. Now, what's not obvious and what we can't prove in this class is that this is actually a complete answer to the question of what are and where are the eigenvectors. All of the eigenvectors are going to, in fact, evidence themselves in this way. And again, that's not something that we the nitty gritty of Jordan form is heavier and deeper than we can reasonably do in this class. So I'm just going to assert this as a given, and we're not going to prove it. But this plays out. Literally, so if you're looking inside of for a given eigenvalue, or said differently, given an eigenvalue block that you want to look inside of, for every eigenvector, there is a corresponding Jordan block. For every Jordan block, there's a corresponding eigenvector corresponding to that first column. Specifically, then also the total number of eigenvectors, well, that's just the number of basic Jordan blocks for a given eigenvalue. Okay, so again, we're not going to prove that fact in this course. But here's how we can capitalize on that. Let's suppose that we know that this is the Jordan form. So this matrix, notice, is not diagonalizable. We have this off diagonal entry. It's not diagonalized. We know there's not going to be 4 eigenvectors. If there were 4 eigenvectors, it'd be diagonalizable. So what we can do, though, is we can say, well, this eigenvalue block here, this 3 by 3 eigenvalue block, has 2 basic Jordan blocks, there and there. And therefore, each one of these basic Jordan blocks has a first column. 2 basic Jordan blocks, 2 first columns, and therefore 2 eigenvectors. Those 2 eigenvectors are, I guess I probably would have called them V1 and V3 are the 2 eigenvectors. Now, don't make the common mistake. A lot of students will get confused and think that, oh, okay, well, that first column is 4, 0, 0, 0, so that must be one of the eigenvectors. No, absolutely not. It's just that these numbers, 4, 0, 0, 0 is what tells you that the corresponding basis vector, whatever it is, actually is an eigenvector. What that basis vector is not evident in the Jordan form itself. Okay. All right. Likewise, down here, this little 1 by 1 eigenvalue block. Well, 1 by 1 eigenvalue blocks are really easy to understand. There's only 1 basic Jordan block inside of it, right? Which of course has 1 first column, and therefore you get 1 eigenvector for that eigenvalue. So grand total, notice as we expected, grand total of 3 eigenvectors, not 4. Corresponding as well to the number of basic Jordan blocks, which is again 3, not 4. Okay, pause for questions. Anybody have questions? Everybody happy? Yeah. Mm-hmm.
Are the non-eigenvectors that corresponding to the columns with 1, do these have any properties?
Yes, they do. We're not going to be able to get into that, but they are nice in some powerful ways, and I'll kind of hint at that a little bit later on when we get into chapter 6. There's some neat things that you can do with that, but it's a little bit beyond what we can do. In past semesters, I have spent some time talking about that, and again, in my continued reevaluation of the course, it's one of those things that just didn't quite make the cut in terms of reward per unit effort. It's not quite up there. But there are some neat things to say about them. Absolutely. So, said differently, all of the Jordan basis vectors, they are all interesting in certain ways. Yeah. By the way, just a cultural note. Sometimes you will hear what I call Jordan basis vectors referred to instead as generalized eigenvectors. That's a term that they use. I don't care for that term. To me, the term generalized eigenvector makes it sound like it's a kind of an eigenvector. And very importantly, they're not. Right? Some of them are absolutely not eigenvectors. But anyway, you're going to hear that term generalized eigenvectors. I suggest that from that you infer, Jordan basis vectors. Okay. Great. Thank you for that question. Just another quick for example. This is really kind of the same as the example we just looked at. So what does this tell me? As this being the Jordan form, what does that tell me about our original matrix A? Well, I see the Jordan blocks. There are correspondingly certain first columns. That's the first column for the first block. That's the first column for the second block. And that tells me that V1 and V3 are eigenvectors. And you can see that explicitly in, again, take these equations, these columns, write down exactly what they tell you about the linear transformation. Now here, notice, those columns are telling me about what T does. I'm writing in the language of the standard basis here. And in the language of the standard basis, we represent T with the matrix A. Okay, so this is just S language, S talk for T of V1 is 4V1, T of V3 is 4V3. But again, writing it in standard basis language, it tells me that V1 and V3 are eigenvectors. Eigenvectors for that matrix. All right? Everybody happy? Okay. By the way, here's a quick callback. So you may recall that when we were first talking about section 5.3, I mentioned that there's going to be a lot of stuff that we're going to do, coming up, maybe now, where everything's going to use this idea of matrices representing linear transformations with respect to bases, and thinking of it as a language and learning how to recognize how one statement in one language is effectively the same as a different statement in a different language. Right? And that's a lot of what's going on right here. Okay. Alrighty. So, couple of quickie points. So we're not going to prove that every matrix can be put into Jordan form, and we're not going to prove that eigenvectors correspond to the columns as I just described. So that all that stuff is just too much for this course. Here's another thing that we're not going to do in this course, because again, it's hard. How to find the Jordan basis? In general, quite hard, and we just don't have time for it, right? So now, a diagonalizing basis is easy. Eigenvectors. We know how to find eigenvectors. We've got a little mechanism for that. It's very plug and chug. Y'all can do it just fine. If a matrix is diagonalizable, find all the eigenvectors. That's your diagonalizing basis. Jordan basis, not so simple. So, sadly, that's unfortunate. Okay. So, sometimes, though, as it turns out, you can kind of clever your way along to finding at least what the Jordan form is. And it's a little bit weird how that works, but let's suppose I have some matrix and this is its characteristic polynomial, let's say. Well, that actually tells us a tremendous amount of information about the Jordan form already. I mean, after all, we know that there is an eigenvalue block with eigenvalue 1. The multiplicity is 2, so we know it's a 2 by 2 eigenvalue block. And so we know it's got this size and shape. And, if you just think about how can you possibly fit blocks inside of blocks, there's actually only 2 possible Jordan structures inside of such a small eigenvalue block. That's it. That's the only possibilities. So it's got to be one of these, right? This eigenvalue of 3, multiplicity 1, well, no surprise, there's only one by 1 eigenvalue block with 3 on the diagonal, right? And that's a pretty easy question to persuade yourself. So with only 2 possibilities for the first block and only 1 possibility for the second, these are the only 2 possible Jordan forms. Right? And even though I can't find the Jordan basis, I can distinguish between these forms just by thinking about how many eigenvectors it has. Here's the basic Jordan blocks. Right? This has 2 basic Jordan blocks, which would mean that there were 2 eigenvectors. Let's see here, color choices. This only has 1 basic Jordan block, which would mean there's only 1 eigenvectors. And this is really easy to arbitrate. Just find the eigenvectors. If there's 2 of them, this is your Jordan form. If there's only 1 of them, then that's your Jordan form. Now, we haven't found the Jordan basis. I mean, how to actually, what is the basis V1, V2, V3? I mean, specifically the V2 vector that would give us this Jordan form. We don't know how to find that. but we can decide which of these actually is the Jordan form by this, simply counting possibilities. Okay. All right. And then just real quick, I want to point out that you can do this kind of thing for larger matrices. There's some homework exercises that go along these lines as well. So let's suppose that your characteristic polynomial is this. Well, you know that there's a 4x4 eigenvalue block. You also know that there is another 3x3 eigenvalue block. Let's look at the 3x3. There's a 3x3 eigenvalue block. And now let's consider the possible Jordan form structures. One possibility is that there is one large basic Jordan block. A single 3x3, and that's it. Now, here's another possibility. It could be that there is a 2x2 and a 1x1. That's another possibility. Right, now here's a third possibility. It could be that there is a 1x1, another 1x1, and then another 1x1, right? I mean, that's a third possibility for what the Jordan block structure might be for that 3x3 eigenvalue block. And here's the thing, in case you didn't notice, by the way, I was sort of pairing up with this arithmetic here. Anytime you have a basic Jordan block structure inside of an eigenvalue block, you can just count how many columns is each one of these Jordan blocks taking up. And notice, of course, the number of columns total has to equal to the sum of the number of columns that each one takes up. So we know there's 3 columns. The multiplicity is 3. So what we're really looking for is a number of different ways that you can add positive integers to make 3. Okay? So you don't even have to draw the pictures to come to this conclusion, since there are only 3 ways to add positive integers to make 3, other than rearrangements, which again, rearrangements we consider to be effectively the same Jordan forms. We know that there's 3 possible Jordan structures inside of, here, let me do it like this. Inside of this factor, inside of this eigenvalue block, there are 3 possible Jordan structures. And now likewise, let's not draw the picture because it's going to get a little ugly, right? But there's a 4x4. I could draw, I suppose, a 4x4, but again, that's going to get out of hand, drawing all the pictures and everything. But notice there's only 5 ways to add positive integers to make 4. These are they. Okay? And so there are 5 possible Jordan structures inside of that eigenvalue block. So altogether, grand total, there's 5 possibilities here, for each of which there are 3 possibilities here, and 5 times 3 is 15. So there's 15 possible Jordan forms, grand total. Okay. All right. Okay. Questions? How we doing? Everybody happy? All right, so we're going to make a little bit of headway now into section 9.1. So first thing I'll say, so we just finished chapter 5. By the way, what we're going to, let me rewind a little bit. Before we get into chapter 9, why do we need to know about Jordan form? What are we going to do with Jordan form? As with a lot of the linear algebra that we learn in this class, we're going to solve differential equations with it. And it turns out that there's a certain kind of differential equation to which you can very naturally associate a matrix. And if you can put it in Jordan form, then from that Jordan form you can infer the solutions to the differential equation. Now, there's a bunch of details that are going to go into that. We'll see that later on when we get to chapter 6. Now, in case you're wondering, wait, I thought 6 came after 5. Why are we going to 9? Yes, we're going to jump around in the book a little bit. The book's choice to put chapter 6 before chapter 9, right? Numerical order, is fine. Nothing really wrong with that. But it turns out that there are some ways in which it's kind of nice to have chapter 9 done first. Not the least of which is, it's just nice to get all the linear algebra done. Why not have the linear algebra done? And then with the linear algebra all done, then we can end the course on differential equations. So I like having, we're going to be using linear algebra as tools, so let's get all of our tools first, and then we'll use the tools. Okay, so jumping for now up to chapter 9, and then we'll go back later to chapter 6. Yeah?
So is the homework on Friday going to be 5.5 and 9.1?
There's no way we're going to finish 9.1.
So just 5.5.
Yeah, must be. I can't remember. It's certainly for today, all we finished is 5.5. I cannot remember which other days count and what other things we've done. You don't think we turned in 5.4?
Yeah.
Oh, okay, so yeah, it should be just 5.5. Because this is not a long section, but it's going to take more than 4 minutes. Right? Okay, so let me just give you a little bit of context. We won't probably get into too many details on inner product spaces, but this is going to be another abstraction. So think chapter 2, think vector spaces. And so let me remind you what the deal was. Why would we go to all this trouble to define this abstract thing called a vector space, in which we sort of stubbornly refuse to talk about what the objects in the vector space actually are. And only forget about what they are, we're going to view them as abstract things, and we're just going to deal with how they behave. Right? So what was the point to that? Well, the point to that was not that we just want to be as useless and abstract as possible. Right? That a lot of people misunderstand, and I gave you all a similar speech back in chapter 2. The point to abstraction is not in defiance of utility, right? From y'all's point of view, anyway, the purpose of abstraction is to make the results that we find apply as broadly as possible. So if you state and prove a theorem about R3, well, that's relatable and concrete, and that's very nice, and it's a safe little world to live in, but you are confined then. Those results only work in R3. And you got to do a whole separate proof for R4, and a whole separate proof for R5, and a whole separate proof if you have a vector space that's not Euclidean, like a vector space of functions, or a vector space of matrices, or, oh my gosh, whatever it might be, right? And so, if the thing that you're proving is ultimately proved by the way things behave, why tie yourself down, burdened also with what they actually are? Right? But what they are doesn't matter. Right? And I give you all these silly examples of, if you have this many apples, right, then you can split them up, and everybody, both your friends each get the same number of apples. Ooh, okay, well, now, but what if we have oranges? Oh, separate question, right? It's a ridiculous observation. Well, come on, let's find the abstraction of 6. And I don't care what they are. 6 is divisible by 2. That's the point, right? And then we're talking about oranges or apples or who cares, right? So we can find this abstraction called a vector space. We've stated and proved theorems about vector spaces in the abstract, and then when we found ourselves at a later date, unexpectedly dealing with a new set of things, and oh my gosh, look at this! It's a vector space. And we instantly had a bunch of theorems that we could just write down and apply to that abstract, to that new, different vector space. So this is how we solve differential equations. One of our main tools for solving differential equations was realizing that it was an example of a certain kind of abstraction. So we're going to make now a new kind of abstraction. Vector spaces came from looking at Rn. Specifically, Rn thought of as a set with vector addition and scalar vector multiplication. Those two operations only. Addition and scalar multiplication. And all of the vector spaces that we saw had to have, therefore, an addition and a scalar multiplication. And we are now going to say, hey, but you know what? Rn also has this thing called a dot product, which is pretty handy in a lot of circumstances, right? So what if we start to notice other contexts, objects, worlds, whatever you want to call them, where in addition to having an addition and having a scalar multiplication, what if also What if it has something that behaves kind of like a dot product, in a way? And that's going to be our thing called an inner product space. Quick reminder, what we meant by behaves like an addition is we wrote down a bunch of properties for how addition and Rn behaves, and then we say, okay, well, anything that behaves kind of analogous to that, we're going to call that good enough, and likewise scalar multiplication. So what we're going to do here is we're going to look at a bunch of properties of how the dot product behaves. Here's our old friend, the dot product. Here's a long list of properties that it satisfies. And we're going to say that anything that behaves, kind of morally kind of like this, we're going to say is an inner product. More on this later. See y'all on Wednesday.